For this lesson, we're going to be doing the equations of exponential functions. And so before we start the equation, we need to remind ourselves of these important exponent rules. When we have an exponent that's negative, that negative exponent will move the thing back down to the denominator. If it was in the denominator and it was a negative exponent, it'd move it back up to the numerator. So it will make it cross the fraction bar. So we saw 3 to the negative 2 became 1 over 3 squared, which is 1/9. But if we raised a whole fraction and we saw that, what we would end up with is flipping that fraction, so that becomes a over 1 to the nth power. Since 1 to the n, anything is just still divided by 1, it ends up just saying a to the n. So that's what we see when we saw 1/3 to the negative 4 power. We flip the fraction, it becomes 3 over 1, and raise it to the 4th. The third property, we have anything to the 0 power is always 1. Doesn't matter what the base is. So this 324 to the 0 power, always going to come out to be 1. The last thing we saw was a rational exponent. Remember, we have power over root. So if I have a power over root, I'm going to convert that back and forth. So when we saw something like a square root, it became 1/2. Cube root became 1/3. This one has a cube root, so it's going to be a 1/3 power, but since x is squared, it becomes the 2/3 power. All right, our main goal is to look at the graph of an exponential function and write the equation. Based off of our parent functions, we've seen where an exponential function has this general shape, and it could be exponential growth or exponential decay. So this one is growth, and this one is decay. That is going to be dependent upon the base of our exponent, so the b value. So we had a general form that was a times b to the x, and b is what will create that exponential growth or decay. A is usually our initial value, or the y-intercept, and this is because if there's no vertical transformation, let's say I plug in 0. Well, b to the 0 power is just 1, so I just get a. So that would mean our y-intercept is usually just 0a. This will change if there has been some type of vertical shift. So if it was moved down or up, that's going to affect where our y-intercept is. B is the base, it's always positive, we know that. So we could have y equals 3 to the x versus y equals 1/4 to the x, but the base is always positive. Then the last one says true or false, 2 times 3 to the x is equivalent to 6 to the x. This is a false statement. We cannot multiply these things together because the 3 is being raised to the power. So that is going to get our exponent, and we always do exponents before we get to multiplication in our order of operations. So you'll never be able to multiply those things together when 3 has an exponent or when the base has an exponent. All right, let's look at some of the basic transformations that we've learned before. If I have 3 to the x, we could graph this by hand, but we just want a general idea. It should hold that same parent shape. Here, let me draw it in red. It's going to hug the x-axis and then grow very quickly. It hits right there at 0, 1 for the y-intercept. And that's because if I plug in 0, 3 to the 0 power is 1. And then we could plug in more points and see what's going on with the graph. But it will have a horizontal asymptote here at 0 based off the parent function. It was not shifted up or down. So the domain stays to be all real numbers with a horizontal asymptote at y equals 0. The range of that function is 0 to infinity. It's not going to equal 0, so we don't get to put a bracket, but it just means that as we get more negative, that fraction gets smaller and smaller and smaller, but closer and closer to 0. All right. Now, a 1/3 exponent would mean that we're doing an exponential decay. So it would look something like this function, but there was a transformation to this. So we shifted it up 2. So we want to take that whole function and go up 2. What that's going to do is also move the asymptote. So the asymptote would have been at 0, but now it's going to go up 2 to y equals 2. Let's go ahead and write out what that asymptote is. The graph of that function is decay, so I could draw in our decay graph, getting closer and closer to that y-intercept, or sorry, that horizontal asymptote. Now the y-intercept here, if I had plugged in 0, let's look at what that would look like. Y equals 1/3 to the 0 power plus 2. Well, anything to the 0 power is 1, so I end up with 1 plus 2 to get a y-intercept of 0, 3. All right, our domain will not change. Every exponential has a domain of 0 or infinity to infinity. Our range does change. It was 0 to infinity because that's what the parent function looks like before we shift it. But because we shifted it up 2, that horizontal asymptote shifted up 2. And that makes our range 2 to infinity. All right. Number 3, we have a few more transformations, but we can see that -5 at the end moved it down 5. But the 2 out front was a vertical stretch. So a vertical stretch by a factor of 2. The 3 is what tells us this is exponential growth. It's not a transformation. So that 3 to the x power, you could circle it and say that is our exponential. That is what's making this an exponential graph. But I'm going to put in our axes and shift our horizontal asymptote down 5. So this would go 1, 2, 3, 4, 5. There's our horizontal asymptote. Y equals 5. It was at 0 because that's what a parent function would do, but shifting it down 5 shifts the horizontal asymptote as well. If I found the y-intercept, let's do that up here at the top of the page. Y equals 2 times 3 to the 0 power minus 5. Think about how we would evaluate that. Exponents would come first, so 3 to the 0 is just 1, which means I'm multiplying that 2 by a 1. So 2 times 1 minus 5. Two times 1 is just 2, so 2 minus 5 is -3. So I'd have a y-intercept here at 0, -3, and we know it's exponential growth, so our function should start to grow very quickly, but it goes towards the horizontal asymptote on the left. That domain will stay all real numbers. The range shifted down 5 because of that horizontal asymptote. Sorry, that should have been -5, which makes this -5 to infinity. So lastly, therefore, when a is greater than 0, it would look something like this. Our graph is either going to go up or down, depending on if it's exponential growth or decay. But a is positive. That means it hasn't been reflected across the x-axis. Its domain is always going to stay negative infinity to infinity, our horizontal asymptote is going to stay with whatever that vertical shift was. So if it was shifted up or down, that C value is going to affect our horizontal asymptote. That makes the range C to infinity. This will change if I reflect it. So it doesn't have an example here, but let's say I had y equals negative 3 to the x plus 5. That plus 5 moved it up 5. So I would take this and go 1, 2, 3, 4, 5. There's my horizontal asymptote. And instead of it going up like this, it has been reflected. So our graph actually looks something like this. So that was the old one. Let's erase or mark that out. And that reflection is going to affect the range. Now the range of this function is going to say negative infinity all the way up until we get to that horizontal asymptote, which is 5. It's not a bracket, it's still a parenthesis because it's an asymptote. But notice the domain didn't change, it's still all real numbers because every x value is going to have an output. Okay, so what we want to do is be able to graph or take a graph and write the equation. If we go off the general transformations, we could do a vertical shift or we could do a vertical stretch or shrink. So we want to find each one of these things. We're going to start by finding C, then move to A, and then B. So this is kind of what we call the CAB method for an exponential function. But based off this, we first want to find C. We're going to find C by identifying the horizontal asymptote. In this function, I see this graph has a horizontal asymptote at -2. Now look at the scale. The y values are counting by 2s. The x values are counting by 1. So that's important to notice. But if I put this in here, it has a horizontal asymptote at y equals -2. So that tells us C is -2 based off of our transformations. Then we can find A. So we're going to find A by plugging in the y-intercept. All right, our y-intercept is 0, -3/2. And if I look at what the general equation was, we had y equals a times b to the x plus c. We just found c to be -2, so I could plug that in. We know that's -2. But we also can plug in our point 0, -3/2 to figure out what a is. We still don't know what b is, but if x is 0, then y is -3/2 based off of that point. Now we can just do a little bit of algebra, and I'm going to simplify. I know that b to the 0 power is just 1. And 1 times anything is just going to stay a. So we're left with really -3/2 equals a minus 2. I want to add 2 to the other side. So we can use our calculator, and I would do -3/2 plus 2, and keep everything in a fraction if we can. So that makes that just 1/2 for A. We still have another piece of the equation we don't know. So I want to find B. And we can find B by plugging in another point. So we always start with our y-intercept of plugging things in, but then we'll go to our other point. Notice we were given another point here on the graph of 2 5/2. So I'm going to say 2 5/2 is the point we're going to use. And let's start plugging things in. So we had y equals, we just found a, it was 1/2, times b to the x minus 2, we found c already. The only thing we need to figure out is what is b. If y is 5/2 and x is 2, then we can solve this out. So it looks something like this. And we want to solve for b. If we do inverse operations, the first thing we're going to need to do is add 2 to both sides, because currently the 1/2 is being multiplied. So this minus 2 is not really touching the b at all. I can go ahead and move that to the other side. That leaves me with 1/2 b squared here. And let's do 5/2 plus 2. 4.5, turn that back into a fraction, I get 9/2. At this point, we have to decide what we're going to do first. We've got 1/2 or that squared, but when we're doing the inverse operations, we're going backwards in the order of operations. So I need to undo the 1/2 first. So I'd divide by 1/2. And I'm left with b squared on the right. So in my calculator, let's do parentheses 9/2 divided by parentheses 1/2. It gives me just 9. So b squared is 9. If I square root both sides now, then b equals 3. And we've found everything we needed. So our whole equation would say y equals a was 1/2 times 3 to the x power minus 2. So that took up a little bit more room than what you were given, but we can find this next example as well on a separate sheet of paper. So in this next problem, number 5 here, again, we're following the CAB method. We're going to find c first by doing the horizontal asymptote. It has a horizontal asymptote. It looks to be y equals 1. And you can kind of see this is halfway between 0 and 2. So it is flattening out here at positive 1. That means in this equation, a times b to the x power plus c. We just found the c. It shifted up 1. The next thing we want to find is a. So we find a by plugging in the y-intercept. So we always start with the y-intercept first as far as the points that we're given. So if you notice you're given 2 different points, you want to use the y-intercept one first. So y equals a times b to the x plus 1. We just found c. Let's plug in 0, 8/9. That's our y-intercept. So y is 8/9, and x will be 0. b to the 0 power, anything to the 0 power is 1, so that's really just a times 1, or a. We still have the plus 1 out there, and 8/9. I subtract 1 from both sides. So a is 8/9 minus 1. 8/9 minus 1 gives me this decimal, turn it back into a fraction, it's negative 1/9. Now we need the last part, find b. And we can plug in another point. 5 negative 7/2, so 5 negative 7 over 2. So far what we have, y equals a, whoops, we already found a. It was negative 1/9. So negative 1/9 times b to the x plus 1. Only thing left to find is b. We plug in that point. -7/2 equals -1/9 times b to the x. And our x is 5 plus 1. If we do inverse operations, we're trying to get b by itself. The first thing we're going to have to do is subtract 1 from both sides. So if I subtract 1, I get -7/2 minus 1 back into a fraction is -9/2 equals -1/9 times b to the 5th. We have to undo the multiplication first, so I'm going to divide both sides by -1/9. So in our calculator, we had -9/2 divided by -1/9. It gave us 40.5. Turn it back into a fraction, so 81/2. And that's equal to b to the 5th. If we want to undo that exponent, we have two options. We can use our rational exponents that we've learned about with radical functions. So I could raise it to the 1/5 power, or we can take the 5th root of both sides. So I'm going to take the 5th root of both sides, and it will look like you say b to the 5th root, 81/2. What that does is cancel out the exponent with the root. So we just have b by itself now. But we would need to figure out what is this 5th root of 81/2. In your calculator, you have a square root button where you can change the index. So if you look right there, I'm going to hit second, that square root button, and I'll have to go back to a 5 there. So 5th root of 81/2. And we get this decimal. If I try to turn it into a fraction, it doesn't work. So this will not turn into a fraction. It's just something that's irrational. So our exact answer is just the 5th root of 81/2. It's ugly, but that's what it is. When we put this all together, y equals a was -1/9. B is the 5th root of 81/2 to the x power, plus c, which was +1. So this is how this came out. It's ugly, but that's what it is. There is potential that you might see this written where it was approximated. So this was approximately 2.096. So if they took this and approximated it, they may have written this as 2.096 for the base of the exponent. Oftentimes we want exact answers, so even if it's ugly, just keep it in this form. Okay, and then the last example here. We have an exponential decay function. So if I plug this in here, CAB, same method. We first want to identify C by looking for the horizontal asymptote. This horizontal asymptote is at +1 still. Look at where your x-axis is, and that hits at 0, 2. So this is halfway, it's +1. So y equals 1. Always check the scale. Y equals a times b to the x plus c. That was c. Then we can find a by plugging in the y-intercept. And y-intercept. Our y-intercept was 0, 2. So I'm going to plug what we have in. In this case, y is 2. X is going to be 0. So 2 equals a we don't know, b we don't know, but it's b to the 0, plus 1 we did find out. 2 equals anything to the 0 power is just 1, so that's 1 times a, that's just a, plus 1. and I subtract 1, I get positive 1. The last thing we need is to find b. We do that by plugging in another point. Okay, our other point is negative 3, 4.5. When I plug that in, y is 4.5, x is going to be negative 3. So a was 1, b we don't know, that's what we're trying to find out, c was actually 1 as well. So I can subtract 1 from both sides. If I subtract 1, I get 3.5 equals 1 times anything, so that's just b to the negative 3. This is where it gets a little tricky, because I cannot take a negative cube root. That would not work. But we learned some things about exponents. So I can raise this to the negative 1/3 power. We want to raise it to a negative because a negative times a negative will turn out positive. And we raise it to a 1/3 because that's the reciprocal of 3. It's the same thing as taking the cube root, since it's a 1/3. So I'm going to raise both sides to the negative 1/3 power and see what we end up with. So that's just b. In our calculator, we have 3.5 raised to the negative 1/3. And it gave us some ugly decimal. So 0.659 was what it was approximately. To really kind of clarify what's going on here, we can use those exponent rules, but it's saying 3.5 to the negative 1/3. A negative exponent flips the fraction, so that becomes to the positive 1/3, and that's a cube root now, so it's the cube root of 1 over 3.5. Now that's still kind of ugly. 1 over 3.5 we could figure out to be fraction, all right, 2 over 7. So if you wanted to make that fraction prettier, I'd put cube root of 2 over 7 equals b. Sometimes they're not going to come out pretty. The final answer for this would be 1 times the cubed root of 2 over 7 to the x power plus 1. It's ugly, but if it was approximated, it would be 1 times 0.659 to the x plus 1. We can see it's an exponential decay because the base of the exponent is smaller than 1, and that's what made a function decay. So you just want to be aware that we can use a negative point, but we have to raise it to a negative reciprocal exponent and use that, because we cannot take a negative square root or negative radical root of a function. Go ahead and try these in the lab manual for some more practice.